Thank you. Thank you, Ken. Hello, everyone from my side as well. As we explained, we've worked together in Evides Industriewater with the AM team to quantify and mitigate laughing gas emissions, nitrous oxide emissions in one of our full-scale plants. We have prepared a few slides to take you with us in this journey. First, a few information about Evides Industriewater. We are providing water solutions for customized water solutions for industrial clients, and that can be processed water for several processes of industries like cooling, but also demineralized water and wastewater treatment. We are focusing a lot in options for water reuse, for resources recovery, and this is also the focus of our research department, R&D, but also we are trying to find ways to optimize our existing processes and minimize the energy use or lower our N2O emissions. And this project belongs to that part of the company. So in general, our environmental policy is that we try to reduce our CO2 footprint, use more renewable energy, and reduce our emissions, and of course, not contribute to water scarcity. So have better recoveries, reuse water as much as we can, and then reduce our pollution to the environment, to the water bodies. So there are ongoing projects for all these fields. And then specifically for the emissions, the greenhouse gas emissions from wastewater treatment plants, the main three contributors are CO2 emissions, methane, and nitrous oxide. And the nitrous oxide, based on literature, is one of the biggest contributor, as we mentioned. But then this is something we have already seen in our specific case, where we have a 2-year campaign, or measuring campaign. We mentioned one because when we started collaborating with AM team, it was 1 year. Now it's been 2 years. And if you see the pie of CO2 contributors for this specific plant, you can see that laughing gas, nitrous oxide, is 50% of the total emissions. And if you take also into account the demon, it's a bit more. Then the aim of this research was at first to quantify the emissions, to know our baseline, knowing what laughing gas is being formed at which moments. Thereafter, to understand why it's being formed. So what are the formation mechanisms and what factors that we might be able to change contribute to this formation of laughing gas. And finally, of course, try to identify mitigation measures and implement them. So a few information about this industrial site. It's a conventional activated sludge system with a denitrification and nitrification. The effluent, even though it's called industrial plant, it is similar to municipal, but it's more concentrated, much more like 5 times more concentrated than typical municipal, and has less COD compared to a municipal. And also the patterns are different. The daily and weekly patterns are different than a municipal plant. And of course, for a laughing gas research, the focus was in the denitrification and nitrification tanks, specifically here highlighted with red. Then the approach followed. First, as we said, we wanted to measure. So we chose for liquid phase nitrous oxide monitoring. That's already happened. Then we followed with data analysis from our side, and also in collaboration with the Brunel University of London, we had a multivariant analysis. And thereafter, we proceeded with model-based root cause analysis with AM team, and with model-based mitigation strategy testing with the AM team. And now that we have found our mitigation measures, that I will come back to them later, we are in the phase that we are trying to implement them in full scale, and thereafter continue monitoring to be sure of the effect. Then, for the measurements, we chose the unison sensors because they measure in the liquid phase. We know that measuring in the gas phase might be more accurate when it comes to the actual emissions estimation, but then if you want to identify mitigation measures, you need measurements inside the water, because you want to know and be able to compare. The moment you see a formation of N2O, what else was happening at the same moment. Because if you measure in the gas phase, maybe what is being emitted in the air at that moment might be formed a bit earlier. Then let's go to the main outcomes. So 2 years of measuring campaign from December 2021 until January 2024. What we have identified, okay, the average formation factor with coincide comes really close to the IPCC number, around 0.016 kilograms of laughing gas per kilogram of ammonia being treated. But this is the average of the year, or the average of the 2 years. If you take different periods, you'll see that at some periods it will be much more, and at some periods it will be much less. So there is a seasonal profile with higher formation when the temperature of the water goes down. So during autumn, winter. And thereafter, we also found a daily profile that it was repetitive, and then a mitigation measure that was identified and tested with a model of AMT. Now, before we go into details of what all this what all these things mean, let's remember what is N2O and how it's being formed during nitrification and denitrification. So here we have nitrification from ammonia to nitrate, and denitrification from nitrate to nitrogen gas. Then you have 3 main pathways. In the nitrification, it's from the order of through hydroxylamine oxidation, when you have high DO and high ammonia loads incoming to your tank, or you have the other pathway that is through AOB denitrification. So when there is low presence of dissolved oxygen and high concentration of ammonia or accumulation of nitrates. And then in the denitrification side, in the heterotrophs are able to produce N2O, but also consume them, because it's an in-between step during the nitrification. But to do this, they need COD, carbon source. And if you have carbon limitations compared to the amounts of nitrogen that are coming into your tank, then you might stop in an earlier step of this process, either stop at NO2 or N2O. And both would end up in the formation of N2O, because also accumulation of nitrite will end up by the AOB denitrification becoming nitrous oxide. So this is how it was formed. And now let's have a look at the daily repetitive profile. So you can see here, well, one moment. Better like this. You can see here the influent water. It's 5 days, and whenever the influent water will go down, also the incoming ammonia, the blue dark line here, will go down as well. But then you will see that the nitrification zone, the nitrate, will go up because it's related to a previous peak of ammonia, since there is internal recirculation. And at those moments, since the incoming influent goes down, also the incoming available COD for the denitrification coming with the new influent goes down, and we need to have an external carbon dosing. And we had that. But then the way it was being dosed, it was not optimal for full for N2O formation. So at certain moments that the COD over N ratio will go low, you will see an N2O peak in the brown line on the top. And that sometimes will happen with any other contributing factor, but sometimes you will also see a dissolved oxygen peak because of a certain situation in the tank. So we realized that the biggest trouble for our process seemed to be the not optimal carbon dosing system, but also it could be partly by the dissolved oxygen or by the seasonality. So then we wanted to realize what is actually happening with some external help, and this is how we went to Brunel University, where they did a multivariate analysis, and their main outcome was indeed there are 3 contributing factors, and the one that has the biggest effect was the C over N ratio, followed by the temperature, so the seasonality effect, and then the dissolved oxygen values. So for the seasonality effect, we could discuss it, but then there are not many things you can do to act on it. But whenever you, at this phase of the knowledge we have in literature, at least, because I know an interesting PhD research that's taking place in TU Delft right now relevant to this subject. We hope for results. But for the other two, we can act on it. We can optimize our carbon dosing, and we could optimize our aeration. And this is how we decided to proceed with AM10 and see how we could optimize it. But first, we needed to do the CFD modeling, where they take into account the physics and the biokinetics, and they recognize the laughing gas hotspots in your tank. And that was quite viable because, for example, in one of the zones, you have the anoxic and the aerobic zone. We saw that in the aerobic zone, we weren't able to pinpoint the best place for measurements. And then after this research, we were able to find a better location for our sensors. And then this CFD model, kinetic model, it gives you the base to proceed to the dynamic model that is based in ASM modeling. Yeah, activate slats modeling, and then include also spatial information. And with this dynamic model, we were able to check virtual mitigations, to test virtually mitigation strategies. Now, let's see the results. The CFD kinetic model. In the left picture, you can see the dissolved oxygen concentration in the tank. Just to remind a bit, these first two lines are, because the water comes this way, that is the inlet arrow, it's the anoxic zone, and it's followed by the aerobic zones. And then you can see that there are very, very low dissolved oxygen levels at these two zones, while the end of the aerobic tank, the oxygen goes, the aeration was higher. And then there was also quite some dissolved oxygen returning with the internal recirculation. And on the right picture, you see in relationship the N2O production and consumption throughout the whole tank from all the pathways. And then we could see some net production of laughing gas that it was caused, for example, by the returning oxygen, so AOB denitrification at the point of the return. Don't be confused by the intense two colors, because these are from the main production and reduction of laughing gas during denitrification. It's around it. Then you also have N2O production due to carbon limitation. And then we could see also N2O reduction due to low dissolved oxygen during aeration, and that's again AOB denitrification. And when AMT took all these parameters together and quantified them, we were able to see that the biggest contributor to the N2O formation in this specific case was the nitrifier denitrification, so AOB denitrification, but from incomplete denitrification and accumulation of NO2. So we will have lack of carbon that will result to incomplete denitrification, that will result to accumulation of NO2, and this NO2 was everywhere in the tank, and AOB could take this NO2 and make it nitrous oxide. Then this is the focus of the results, only focusing on the AOB denitrification and hydroxylamine oxidation pathways. And you can see the peaks of AOB denitrification that they were mostly here, that we were going from a low to a higher dissolved oxygen concentrations. And as a total amount, it was much higher compared to hydroxyl oxidation, that it happens partly in the end of the tank. And we proceed to the dynamic model, where you can see the model's prediction with the two lines, while the dotted green points are the actual data of those days. And the model with our actual data had quite a well fit, even though the model overestimates the formation. We thought that for the purposes of our application was good enough to proceed to test mitigation measures. And then you can see here that there is no actual measurement happening, but also the model does a prediction information that there was sufficient carbon to consume all the N2O and become nitrogen gas. While here that we had the peak of formation, it will be we will also see a carbon limitation in the water based on the model. And thereafter, we decided to test different scenarios. So on the left graphs, you can see the carbon dosing trends we tested. First one being the base case. Then the middle graphs are the laughing gas concentration. The model is the continuous line, while in the first graph of the base case, the orange dots are the actual data. And then you can see the carbon dosing need, so the amount of carbon that we had to dose per day, and the expected emission reduction compared to the base case in the right bottom graph. The most interesting scenarios, and I'm going to focus a bit on them compared to the base case, was scenario 3 and scenario 5, where we would dose carbon in relevance to the amount of nitrogen coming to the denitrification zone. And in scenario 3, it will be just related to the amount of nitrogen coming to the denitrification zone. But in scenario 5, we decided to also include the COD that is coming with the influent. Because in scenario 3, we would end up to having to use more carbon compared to the actual base case, while taking into account what's coming with our influent, result in reducing also the carbon use by 10%. And these two scenarios resulted in 88, and actually for the last scenario 5, to 80% reduction of the N2O emissions. And you can also see the patterns that it's compared to the base case, how much reduced the laughing gas formation is. And finally, this is extra related to 10 to 15% effluent, total nitrogen in the effluent reduction. So conclusions and next steps. We have also realized, as we mentioned, that laughing gas can be reduced, but never can be to zero by taking good care of your bacteria. So you have to avoid having peak loads or too high or too low dissolved oxygen and sufficient COD. But also we have realized that N2O formation is plant specific, and you need to measure in your location to understand what's happening. For our specific case, incomplete denitrification in combination to AOB denitrification were the main pathways. And with the help of AMT modeling, we were able to validate our expectations of why we have formation, and to test mitigation strategies that result in an 80%, and find out which is the most optimal one, and that result to 80% laughing gas emissions reduction, 10% of reduction of external carbon dosing, external carbon dosing, and then finally 10 to 15% effluent reduction in the effluent total nitrogen. So the next steps is to upgrade our carbon dosing installation and evaluate, and we are right now working on this. And we proceed with research in our other Evides Industriewater locations. So that was my presentation. Thank you for your attention.